Imagine driving on the highway while your battery gains charge. Sounds like magic, right? Let's test that magic with very simple math. What are the charging roads? Charging roads put coils under the asphalt. Your car has a receiver. When you pass over a short segment, power transfers wirelessly into your battery. Segments only turn on when a verified vehicle is above them. So how efficient is it? Real-world wireless systems are usually 85 to 93% efficient at the coil-to-coil step if alignment and temperature are good. Overall, grid-to-battery efficiency will be a bit lower because of electronics and battery charging losses. Simple takeaway is expect a little worse than a plug. So what is the typical power levels? For the passenger cars, we are looking at 7 to 11 kilowatt receivers. For buses and trucks, 25 to 70 plus kilowatts using multiple receivers. Higher power helps a lot, but it costs more and needs more grid capacity. There's one formula you need to understand here. Energy gain per kilometer is equal to the power divided by speed, meaning kilowatt hour divided by kilometer per hour. That's it. Say it with me. Kilowatt hour divided by kilometers equals to kilowatt divided by kilometer per hour. So here's a quick example. A car with an 11 kilowatts receiver at 100 kilometers per hour is going to receive 0.11 kilowatt hour per kilometer. Many EVs use about 0.18 kilowatt hour per kilometer on highway. So you cover 60% of what you're spending. You still slowly net lose unless power on the road coverage increases. For trucks, 50 kilowatt receiver at 90 kilometers per hour is going to give you 0.56 kilowatt hour per kilometer. If a heavy truck uses 1.2 kilowatt hour per kilometer, this covers almost half of its need. For bus lane, imagine 25 kilowatt receiver at 40 kilometer per hour. It is around 0.63 kilowatt hour per kilometer. Slower speeds help because you sit over each coil longer. So how much road must be electrified? Take your car that uses 0.18 kilowatt hour per kilometer and gains 0.11 kilowatt hour per kilometer on powered sections. To break even, coverage equals to 0.18 divided by 0.11, which equals to 164 or 164%. It means that it's not possible. So with 11 kilowatt receiver, you can't sustain charge on a full speed highway unless you raise power or slow down. If the car had a 25 kilowatt receiver at 100 kilometer per hour, it's going to receive 0.25 kilowatt hour per kilometer. And the break-even coverage, it's going to be equal to 0.18 divided by 0.25, which is showing 72% of the route. The dynamic charging works best where you control the route, like busways, depots, key city segments, not everywhere. Let's build a small model. Numbers are just for intuition. Assume $3 million per kilometer to build one powered lane, which includes hardware plus roadwork. Spread that over 20 years at 5% interest. Rough annual cost is around $240,000 per year. Now, how much energy does that 1 kilometer deliver? In a busy city corridor, if 10,000 EV passes each day, each of them gains 0.11 kilowatt hour at 100 kilometer per hour. And daily energy equals to 1100 kilowatt hours, which equates to a yearly of 401,000 kilowatt hours. The cost per delivered kilowatt hour is equal to around 60 cents per kilowatt hour before maintenance and electricity. This is high, but in the ballpark of some public fast chargers' price. In moderate use, if 2,000 passes is done daily, it's going to equate to 80,300 kilowatt hours in each year. The cost per kilowatt hour is around $2.99 per kilowatt hour before OEM and energy expenses. Too expensive unless you get much more traffic or higher power per vehicle. So what are the pros and cons? Pros are charged while moving, smaller batteries possible, great for bus lanes and public transportation, shuttles, less peak demand at stations if energy is spread along the route. So what are the cons? Expensive to build and maintain across long highways. Efficiency is a bit lower than plugging in. works best only where vehicle reliably pass high throughput is key. Snow and ice, alignment problems, and speed affect the performance of this. So does it make sense? Yes, but selectively. For fleets and specific corridors, yes, but not everywhere. If you want a one-page summary with these formulas and an example, the link is in the description. You can download the sheet. Thank you.